So now transconductance amplifier. So you know transconductance is given by G. We use the symbol G, or sometimes we use the symbol GM. Transconductance is given by I by V, current by voltage. And you know, it is just like your gain. So output current by input voltage. Current I'm measuring at the output circuit. So output side I'll be having a current source. And input I'm measuring the voltage. So in the input side I'll be having the voltage source. Voltage source means series resistance. Current source means shunt resistance. And cross multiply I naught equal to Gm into Vi. That is the current source value. Current source parallel to R naught, parallel to RL. And voltage source series with RS, series with RI. Is this diagram clear from the equation? See, we are doing this for the third time. Voltage amplifier we did, current amplifier we did, now transconductance amplifier. So here you see input side I'm going to have a Thevenin's equivalent circuit, output side I'm going to have a Norton's equivalent circuit. Because the parameter what I measure is transconductance. See, this amplifier, I supply input in the form of voltage, but output current is being amplified. So you see there is a transfer of parameters. See, in previous two amplifiers, the same parameter was amplified, right? But here you see input voltage I give, but output current is amplified. There are applications which demand these amplifiers also. That's why we are studying about all the four combination of amplifiers. So this amplifier you see at the input side, you will have a Thevenin's equivalent circuit. At the output side, you will have a Norton's equivalent circuit. Here you see the output current is proportional to input voltage. So the ratio is called transconductance. So I naught is proportional to V in, or I naught equal to Gm into V in. This Gm is called as transconductance. Again, this Gm is independent of Rs and RL. So the gain should not depend on the circuital parameters. So the source resistance and load resistance are the parameters you have here. So my gain should be independent of these two parameters. And you know the condition for Ri and Rs, Ri and R naught. Whenever you have a Thevenin's equivalent circuit, Ri should be the largest because it should draw less amount of current. Whenever you have a parallel circuit, RL should be the least because it should draw more amount of current. That condition is satisfied here. See, maybe the way of writing is different. Ri is very much greater than Rs, and you can write RL is very much less than R naught. They have written R naught is very much greater than RL. Both are going to be correct. Okay, so an ideal transconductance amplifier must have infinite Ri and 0 R naught. Sorry, both are infinite here. Infinite Ri and infinite R naught. Only when both are infinity, they can draw maximum power and they can transfer maximum power. That is why the reason given, see, Ri is very much greater than Rs and R naught is also very much greater than RL. So this is the parameter for transconductance amplifier. Any queries? This is the third amplifier type we are studying. See, if you relate and study all these things, it will be very simple for you. If you these type of things, when you learn, you should learn them parallelly so that you can identify where is the difference in circuit and how is the parameters changing. See, the same thing, if it is Thevenin, my RS is becoming very much greater than RS. But the same thing in Norton, it is becoming opposite. So you can come to a conclusion, right? So you can conclude that whenever you have a Norton's equivalent circuit, my input impedance has to be very, very less. Whenever I have a Thevenin's equivalent circuit at the input or output side, corresponding resistance value should be larger. See, all these small things you come to a conclusion only when you understand the circuit clearly. The last thing is trans resistance. It is given by Rm, and resistance, as per Ohm's law, R is equal to V by I. So it is V naught by II. And output side I measure voltage. So output side you have an Thevenin's equivalent circuit. Input side I measure current. So I have Norton's equivalent circuit. IS parallel to RS parallel to RI. And cross multiply V naught equal to Rm into IA. That is the current source value. Voltage source series with resistance R naught. You will have your usual load resistance RL. Across RL, I am going to measure the output voltage. So here you see trans resistance amplifier in which the input circuit is not on and output circuit is Thevenin. And you can say V naught is proportional to I in, or V naught equal to Rm into Ia, and the proportionality constant is going to be the trans resistance Rm. The proportionality constant is going to be the trans resistance Rm, and same way this Rm should be independent of Rs and RL. You know trans resistance, so the unit is going to be ohm. For trans conductance, the unit is ohm inverse or mho, or you call it as Siemens. For voltage gain and current gain, you don't have any unit. You use sometimes dB for representing your current gain. Voltage gain also you use dB for quantifying your voltage gain. So voltage gain dB, current gain dB, trans conductance mho, trans resistance is going to be